taking a look at 914 class notes, resonance practice, letter C. So here's the structure drawn. That's called a nitro group, which you guys have done. You guys have done that Lewis dot structure before. One thing you should always do with resonance structures, really with anything, is actually two things: add in all the lone pairs and number everything. Right? Add in all the lone pairs and number everything. So I'm going to do that now. All right. So I've added lone pairs to everything that needs them, and I've numbered everything. So now you got to start thinking about, well, resonance structures means how do electrons move within a molecule, right? How are electrons shared or spread out within a molecule? 4 rules. You only move, like the atoms don't change positions. You never break sigma bonds. You only move lone pairs or pi bond electrons. And what was the last one? Balance your charges, right? So net overall, this is neutral, but there's a minus and a plus. So the easiest one to look at that maybe people have noticed before is I want to start my arrows at electron density. That's the easiest one for me to see, so that's what I'm going to do first. So I'm going to grab the oxygen 7, I'm going to move these electrons here towards the nitrogen, and then at the same time, I'm going to break that pi bond. Notice, lone pairs next to an atom, doesn't matter what atom it is, that has a p orbital. In this case, it's using its p orbital for a pi bond. Another example is this was in A of this, where you have an sp2 hybridized carbocation, which of course has a p orbital, but that p orbital is empty, right? So lone pairs next to something with a p orbital. That could be a carbocation, or it could be something using a pi bond. So move these 2 electrons there. That's going to create a new pi bond between oxygen 7 and nitrogen 8. The pi bond between 8 and 9 breaks. So that's going to look like this then. All right, back, drawing the resonance structure. Now there's a pi bond between oxygen 7 and nitrogen 8, and the pi bond that was between 8 and 9 now is broken. So that's one set. You can actually do another type of resonance structure. That would involve the pi electrons in this ring. Right? Notice this nitrogen's electron deficient, right? It has a plus charge, has 4 bonds. We can actually push electrons towards something that's electron deficient as well, right? Just like you did here, right? You push electrons towards the nitrogen because you're like, oh, that nitrogen's electron deficient. I should push electrons towards it. Same idea here. Let's take these 2 pi electrons and push it towards that nitrogen, right? Because it's electron deficient. Now, why can I do that? This nitrogen has a p orbital, doesn't it? And so does this pi bond. They're right next to each other. There's a p orbital system, a pi bond system there. So let's move those 2 electrons. Draw those 2 in. Those 2 are going to go right there. Then I also must break that bond. Resonance arrow. Where will there be a plus charge now? Carbon. Who lost electrons? Who lost a bond? Carbon 2. You see that, right? The electrons literally moved away from carbon 2, so there should be a plus charge on carbon 2. What element got electrons? Well, the nitrogen got electrons pushed towards it, but the end, right? Notice how resonance arrows, it flows in a direction, right? It flows in a direction. All right, we're back. So now we have this drawn. So notice we broke the pi bond between 1 and 2, so now carbon 2 is actually a carbocation. Is there still a p orbital on carbon 2?
No.
Yes. Because what's the hybridization state of a carbocation? sp2, right? And this empty orbital here is a p orbital, right? So we have a p orbital system, right? All these p orbitals are lined up. That's what's going on. So we formed a new pi bond between carbon 1 and nitrogen 8, and we broke a pi bond between oxygen 7 and nitrogen 8. But we got to remember our rules, right? So where is there still a plus charge? Nitrogen 8 still has a plus charge. Oxygen 7 now has a negative charge, right? And once you're in this ring, then you're just pushing electrons around a little bit more. So what's the next set of electrons I should move?
Break between 3 and 4.
Yep, I'd break what between 3 and 4? The pi bond. So I move, right, because what are the rules? I move pi bond electrons. And where would there be a plus charge now with this? Where would there be an empty? Carbon 4 would be empty. There would be an empty p orbital now on carbon 4. So a good piece of advice when you're doing resonance structures is if something's not involved with the arrows at all, just redraw it. Right? So this whole part up here after this arrow has nothing to do with this. So you just got to make sure you redraw this correctly from the next one, right? So be careful to focus on which part is actually changing. right? Which part actually has electrons moving, right? So for this arrow, has nothing to do with this. This is just going to be redrawn exactly as it is now. So after this last move, we broke the pi bond between 3 and 4, right? Empty p orbital, because this is a carbocation, right? So it has a p orbital, and 3 sp2 orbitals, right? And there's, of course, there's a CH here that we just don't draw in, because we're lazy, organic chemists. Pi bond between 3 and 4 breaks. Those 2 electrons move here. That forms a new pi bond between 2 and 3, which leaves 4 without electrons, hence a new carbocation and a new empty p orbital. So then the last one, which will look very similar to this, would be these 2 electrons here moving there, and then you'd have a plus charge on carbon 6, right? So this is a good thing to realize, right? Why does this matter? Blah, 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 blah. So you start to recognize, well, certain types of groups pull away electrons from the ring. Right? So that's how we're going to apply this later on. Certain types of groups pull away electrons from the ring. Some groups push electrons into the ring. Some are electron withdrawing groups, some are electron donating groups. So that's how this is going to matter a little bit later on. So at the end of the day, resonance structures are all, they're going to become more important later on, but resonance structures are all just like little mini snapshots of a molecule at any one time. It's trying to help us understand how this molecule behaves, right, during, most of the time. Some are better than others, right? So the first one here is probably, right, just the starting compound is probably the most reasonable one, right? Because there's less charges, right? There's another reason you don't know yet, but there's a plus charge in the ring. So this is probably the best, like the most, that's how it normally sits. But knowing some of these other kind of states, it helps us understand how it might react and behave. Right, so it's just a matter of seeing the molecule in different ways. That's what resonance helps us understand. It helps us understand how it reacts or doesn't react. So again, we're going to talk about some resonance here, and right, the importance of resonance really is understanding reactions. Right, so resonance helps us understand how and why some reactions take place and others do not. Right, it's one of the key concepts to helping us understand those ideas. Right, size, electronegativity, hybridization state, induction also do that, but resonance is another tool, another concept, idea that we use to understand why something does or doesn't happen, why a reaction does or doesn't happen, bonds break or bonds don't break. Or in this case, why is this OH bond, or why is this more a stronger, lower pKa acid than this? Right, initially you'd probably look at this and say, well, oh, OH bond to OH bond, that's pretty even as far as electronegativity and size go. Some of the more savvy among you may look at this and say, well, wait a second, that's an oxygen here. These are just carbons here. Maybe inductively, this would pull more, so this would be a more polar H bond, just by looking at the starting materials. Somebody might have thought that, they should have. That's so induction is one way you can look at this too, to justify this, why this is a stronger acid than this, so induction would work. Another thing to look at would be resonance structures, right? Resonance structures you actually could do resonance structures of the star material, but we really focus on resonance structures of the products, the conjugate bases. So, anytime you're put with an acid-base kind of question, or any reaction, write out the potential products and take a look at those. Because usually, maybe something in the potential product says something about their inherent stability or lack of stability that will clue you in on why one star material might react more than the other. So in this case, let's draw the products. All right, so drew out the conjugate bases for both, including H+, which is just the oxygen this bond being broken. You could look at it as this, right? These electrons going there. All right, so you have an H+, of course you have to balance our charge. So there it is. So we have two resonance structures. Both these conjugate bases can do resonance. The difference is, right, so that's good, right? In this case, resonance stabilizes these because we're spreading out a charge. That'll make something more stable in this case. Not always, but in this case it does. Spreading this charge out. So which one can do it better? That's the tough part. So that both can do it, and now it's a matter of, so resonance alone will not give us the answer. We got to maybe look at some of those other things we've learned. So if I just draw a quick...
Is it because oxygen stabilizes better?
Oxygen does stabilize what better?
The negative charge?
Oxygen stabilizes negative charge better, so I'm drawing two resonance structures there for both of those. And the reason it stabilizes negative charge better, of course, is because, I'm just going to move it over here. We're going to zoom in. Go away. what do we get? Resonance arrow, of course. In one of these cases, we have a negative charge on a carbon. In the other case, we have a negative charge on an oxygen. Right? This is still good. It's just not as good as this, right? Oxygen with a negative charge, with carbon with a negative charge. This is even more stabilizing, right? So it's like layering resonance and electronegativity on itself. So that's why this is a stronger acid, a more reactive acid, with a lower pK. Let's take this one all the way back. So at the start, I could have told you maybe this is the more reactive acid right here. All right, I could have said, yep, this is the more reactive one. Why? I can see literally 3 ways you can answer this. The first way you could say, well, this bond right here is more polar OH bond than this OH bond because there's an oxygen, which is electronegative, that's pulling away electron density and making this a more polar bond than the carbons. That's one. That's using induction. Awesome. 2, you could have said, well, the products of both of these have resonance structures. And I know, right, in this case, resonance is being used to spread out that charge, which I know is stabilizing the products, right, which would be a good thing. And then I take it a step further. How do I differentiate these two based on that? Well, one of them has a resonance structure. One of them has resonance structure where the oxygen has a negative charge in both cases. Whereas this one has one resonance structure with an oxygen with a negative charge, and all the other ones have carbons with negative charges. Well, oxygen is more electronegative than carbon. That's why this would be a more reactive acid. So you literally could use all 3 answers. So let's talk about induction quick. So in this case, we're looking at, right, which one's the more reactive acid, the stronger acid. So we're looking at these OH bonds. With induction, we're looking at how does something affect the polarity of this bond through bonds. So we need to look at the electronegativity of these things, not the size. Electronegativity is the key for the induction, not size. Size matters for boiling points, like polarizability, but in this case, it's all about electronegativity. So we look at the table and say, well, fluorine is higher up in the period than chlorine. So that means it's more electronegative. So fluorine is going to have a bigger induction effect, making this bond more polar. So this would be the more reactive acid there, right? Induction is about electronegativity. With melting points, right, which one of these would have the higher, or boiling point, which one of these would have the higher boiling point? That would be this one. Because that one's size matters, and it's more about polarizability, right? How squishy can it be and form more intermolecular forces.
Wait, can you talk it?
So induction, it's all about electronegativity, right? That's going to pull more electrons through here and make this bond more polar. If I asked which one has the higher boiling point, though, now that is not about electronegativity, that is about size. And of course, chlorine is larger than fluorine, and therefore it's more polarizable, kind of a more squishy thing, so it can have a more of a dipole between 2 molecules, right? It's about that. So this would have the higher boiling point, but this would be the more reactive acid. So we're going to try a Newman projection, and this is going to be very similar to one they made you do in sapling. And so I'm going to try to force things for you a little bit, make it harder than we necessarily want to be practiced. So wedge and hatch drawing. Immediately you should look at this and see that the thing that's in the plane on carbon 1 and then one thing that's in the plane on carbon 2 are how many degrees apart? 180. So we know that this is going to be staggered or eclipsed? Staggered. So we automatically know it's staggered. That's good. So we can maybe write ourselves a note. Staggered. That could be a +1 on a test. Just writing staggered.
Seriously?
Wow.
Well, I hope so.
Right?
I'm all right.
Now, from here though, we look at the instructions. So the instructions say, we want you to look down C2 to C1. So that means we want our eyeball on C2, looking towards C1, which is a little different. So our eyeball is going to be actually over here on this side, right? So it's a little different, maybe not the way we want to do it, but that's we're doing it. So what does that mean then? So what's on C2? So C2 has an H, an iodide, and a fluorine. So if I'm looking down C2 and I have my hands up above my head, something, is something at my feet or at my head? Feet. And what's at my feet? H. So that would be right here. There would be an H there, right? And there'd be something here and something here. What's on my right hand? If I turn, F,
Yep. Because you gotta look at it.
right? I'm looking at it this way, from 2 to 1. So yep, I'm turning to my right. So I always like to turn one direction. You don't have to do it that way. That's just the way I have to do it.
So we can have the eye over there and be okay.
Iodine.
So I put the I over, so then I'm gonna put, in this case, the I is gonna go over here.
Yep.
And remember, it was staggered, so that I should be able to draw in the back one already. Just for, this is 2, and then this big thing, that's 1, right? The big carbon's 1. As I look down here again, now I'm moving my eye past carbon 2. What's at, is there something at the top of my head or the bottom of my feet? Head, and what's that? The CL. What, and my hands are down now. What's in my left hand? Bromine, and that's gonna be to my left. Right? And then what's in my right? OH. OH.
Because you keep your wedges together.
Keep your wedges together and you keep your hatches together. If I split this down the middle, notice the iodine and bromine are both wedged. That's a good check. The F and the OH are both hatched. Good check. We're split down the middle. So now we're going to rotate this. Which carbon do you guys want to rotate about? 1 or 2?
2.
So one has to rotate and one has to stay. One doesn't move at all. So if we rotate, we're going to rotate 60 degrees. Do we want to go clockwise or counterclockwise? Clockwise. So we'll go clockwise. And let's rotate 2. C2. C2 clockwise 60 degrees.
Okay.
So we rotated clockwise 60 degrees. That's what that angle would be right there. Right, 60 degrees. So if we were staggered before, after a 60-degree rotation, we're going to become eclipsed. Right? So we draw this like so. So these things are eclipsed. So everything moved to the right 60 degrees. So iodine is now on top of the chlorine.
Does it matter if it's on the left here or can it?
So I mean, just to draw an eclipse, right? You can put it over here as long as it's on top as best you can.
So you'll still get a split.
So we just
Yeah,
kind of
I'm not-
estimate it's 60
You want to make it very clear that they are eclipsed. You could even write eclipse now to make sure I know.
And then we go.
But you're not gonna take points off it if it's on the left or the right side, as long as they're on.
As long as it's eclipsed, it's fine. That's not that important to me. As long as you indicated to me that it's eclipsed, that's important. Right? So now that's eclipsed. And if we did another 60-degree clockwise rotation, right? Clockwise again. Right? This is carbon 2 and the big one's carbon 1. The back doesn't change at all. And we just move it 60 degrees. So we go from a eclipse now to a staggered. Okay, so after that 60-degree turn, we went from eclipse to staggered. So 60-degree turn, the chlorine, the OH, the bromine, of course, didn't move at all on carbon 2. Whoops, I've changed those around. My bad. Got to keep that consistent. This is carbon 2. This is carbon 1. That'd be tough to work with. So again, we're going to rotate carbon 2 one more time. One more 60 degrees. So we're going from eclipse again. Now we're going to become staggered. Yep, that's wrong. Staggered. Now we're going to become eclipsed. So then the last turn, we went from a staggered, another 60-degree turn clockwise would get us back to being eclipsed. Someone could ask, well, which one of these is the highest energy one? I have a favorite right now. So if I labeled these A, B, C, and D, the highest energy one is certainly going to be one. It's between two of them. It's between B and D because they're both eclipsed. And then I would say B is probably higher energy because iodine and chlorine are pretty big. I mean, I don't know for sure. It's not that I just made this up at the top of the head. BR and fluorine's bad too, but you know, INOH isn't great either. So obviously it's between these. Obviously it's between these two. You want the biggest things away from each other. All right, let's take a step back and now go back to this original drawing and let's draw a different Newman projection and not look at it down C2 to C1, but look at it down from C1 to C2. So now our eye will actually be in red looking down 1 to 2. Right, so ignore this part. We're going to look down 1 to 2 now. So we'll start off drawing our Newman projection. Now, if I'm looking there, if I'm standing there, do I have something at my head or at my feet? Head. So, of course, we already know, right, that these are the things in the plane, the chlorine and the H are, of course, still 180 degrees apart. So we know we're going to have what kind of Newman projection for sure? Staggered. And the question is, the thing I'm looking at, is there something at my head or my feet? It's at my head. So I'm drawing a CL here. So the CL will be there, and that means the other things are down to that way. So if I'm standing here, what's at my right hand? The BR. And at my left hand would be the OH. If I extend now, looking down here to carbon 2, is there something at my head or my feet? Hopefully it's at my feet. That would be the H. So what's up to my right? I. And up to my left is F. Very good. So this would be carbon 2, or no, gosh darn it. Carbon, we're looking on carbon 1, and then the back carbon is carbon 2. Right, so it really does matter which side you look from, right, to get these things. So let's say you have a cyclohexane structure like this, where you have 3 substituents on it. So this OH is trans to the Cl. I would call this OH be on the top of the ring because it's wedged. I like thinking wedge is top, and the hatch being bottom, so it's opposite sides. But this Cl3 and the methyl, these two things are cis to each other. They're both on the same side of the ring, and I consider this the bottom part of the ring, right? Now when I try to turn this into a chair structure, I can either do it one of 2 ways, right? Because every cyclohexane ring like this has 2 chair conformations, right? They could do flips, right? They have one of 2. What I like to do is arbitrarily set the numbering, right? So when I usually, unless I'm doing nomenclature, this numbering is just me making it up and doing what I want. So I'm just going to put 1, 2, 3, 4, 5, 6. I'm going to draw this chair just because whatever. I'm probably going to have to do both anyways, so, right? I'm going to call this carbon 1, 2, 3, 4, 5, and 6. So on carbon 1, right, every carbon in the chair has 2 positions, axial and equatorial. Right? One of them's up, one of them's down, but it's not like axial's always up, right? Or always down. So this chlorine, I like to think of that hash as being down. And I had it on carbon 1. So on carbon 1, what position is down? Axial or equatorial? Equatorial. So I'm going to draw this as that Cl. There's nothing on 2. Carbon 3 is also down. What position on carbon 3 is down? Axial or equatorial? Equatorial again, and it's to the right.
Is it because of the slant?
Yep, because of the slant. If I split this in half, I didn't draw it that well, but this is to the left or this is to the right. So remember, splitting it in half is different than top and bottom, right? Splitting the ring in half is different than top and bottom. There's right and the left, and there's tops and bottoms to the ring. And that's not a CL, that should be a CH.
Can the
3.
3 and the 6 be different? Like, let's say I draw this line longer.
Yeah,
Does that matter?
usually the 3 should be to the right. In this case, whatever this carbon is should be to the right. This should be to the left.
Okay.
Yep, try your best to practice that. So we're not worrying about 4. 5, we have an OH, and it's on the opposite side of the ring. It's up. And on 5, what position is up? Axial or equatorial? Axial. Yep, very good. So now we should be able to do a ring flip, right, of this. Does that mean the ring was kind of leaning to the right here? Now it's going to kind of lean to the left, right? Because we're going to pull one down and make that what was the head become the feet. What was the feet become the head. Number of carbons, so 1, 2, 3, 4, 5, and 6. So what was axial or what was axial becomes equatorial, and what was equatorial becomes axial. But if you're down, you are always down. If you're up, you are always up. So here the Cl is equatorial and down. So now it will be still on carbon 1, except it's going to be axial and down. Carbon 3 had something that was equatorial, and now that's going to be axial and down. And carbon 5 had the OH group that was axial and up, so now it needs to have the OH group equatorial and up.
So why are we doing a flip?
So we just did a flip to see which confirmation, and they might just be asked to do it, right? So the point also here is you could have originally, from here, you could have also just originally drawn this one.
Yeah.
That wouldn't have been wrong, right? You could have drawn this first. Because every single one of these has 2 chair confirmations. So usually when I ask this question, I usually show this and say draw one and then flip and draw the other. I arbitrarily picked, so I look at rings like this and say, if it's wedged, I consider the top part pointing up in the ring.
I mean, we
If it's hatched, I decide it's down. And I just call this number 1, 2, 3, 4, 5, 6. And then when I did my ring, when I draw chairs, I always make this number 1. That's arbitrary. I just remember before I put anything in, I just numbered 1, 2, 3, 4, 5, 6. I could have said 1, 2, 3, 4, 5, 6. It would have been fine. You could do it that way too. Right?
Why is it equatorial?
So why would
So
you do
the way
axial?
I did it, it is equatorial. I could have also drawn it in a confirmation at first where it was axial too, right? So it doesn't matter which one of these you do first, right? You could have drawn this one. You could have drawn this one first and been fine too.
So it's like whatever.
As long as it's down, right? As long as it's on the same side as the CH3, that's all that matters,
Okay.
right? Because so both of these confirmations are okay. I just always draw this one, that one first. Nothing's wrong with it.
I guess my main confusion came from when you were drawing the first structure. Why is it not possible for one in that one position for it to be axial down and equatorial up?
The way this chair is drawn, it only has axial up, equatorial down.
Yeah,
So if I call that carbon 1, then the chlorine has to be in a certain spot, right? So I'm just arbitrarily calling this carbon 1. I could have called any of these carbon 1 and numbered accordingly. And then the other big question is which one's more stable conformation? So if I said B or A, the most stable conformation would be A. I want less things axial, right? Less things axial, right? When things are axial, they have this 1, 2, 3 diaxial interaction. So I want less things axial. Big things we want equatorial. Less things axial for a lower energy conformation. So this would be higher energy, this would be lower energy. So a good old nomenclature problem. So first thing you gotta do is find the longest parent chain. So in this case, it could be, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Shoot. So I could do it this way in the blue, or I could do it this way in the red. One is better than the other. Red is better.
Because it's the larger one and the lower number.
Same number, so they're both 8, right? I said 8? Yeah, they're both 8, but you want to have your substituents have the lowest number possible.
Oh, yeah.
So from here, it would be 1, 2, 3. From here, it'd be 1, 2. So the red is better. So it's going to be octane. Our numbering will be 1, 2, 3, 4, 5, 6, 7, 8. So what do we have on it? We have methyl. So we have 1, 2, 3 methyls. So we have 2, 4, 5 trimethyl.
And then
3 ethyl.
And then a 3 ethyl. And then to put it together, E comes before M, so it would be 3 ethyl, 2, 4, 5 trimethyl.
Octane.
That's right.
are
Now
you gonna give us problems that are on the homework with things that are like turd?
we've done. No, I didn't go over turd or isopropyl this year.
Because there were a few things that were on there.
Yeah, there was like
Sapling, I was
There's
Try.
like a tantrum.
Methyl
Yeah.
octane.
I had to look it up.
It's just boring.